Good morning, everyone. I'm Feruglio, PhD student in aerospace engineering at Polytechnic Torino. The topic of this presentation is nano-satellite functional verification. I'm going to present a simulator technology that we developed to carry out a lot of tests for our CubeSat Symposium. Before I begin, let me thank you, Swiss Space System, for allowing me to be here today. The outline of my presentation, I will briefly describe our CubeSat. Then I will proceed in describing our simulator technology, highlighting a few key features, then guiding you through a brief user interface description. Then I will pass describing all the simulation architecture that we can perform with this simulation, and then a few comparisons and results. This is the picture of our integrated CubeSat. It's an educational project, very low cost, and as you can see, common features, solar panels. One side of the CubeSat is completely occupied by the antenna deployment system, which has been developed in-house, and also sports and network fiber. Going in the inside, as you see, it's composed by 4 main boards. Maybe the most important one is the active altitude determination and control system, which is the payload of our mission. It's in-house designed and consists in 3 magnetic torques for control and has an inertial measurement unit with magnetometers for determination. Processor is an ARM processor. And it's the second board from the top. Going to the common data handling system is a commercial one and based on the MSP 430 processor and also a real-time operating system. ComSys is another board we developed in-house and allows for 1200 bit per second rate in the amateur frequencies. We also implemented a beacon transmission in case of loss of communication with the common data handling system as a fail-safe. Then the electrical power system board, commercial, 20 watt-hour battery capacity, and provides regulated and unregulated buses. I need to say that the development of STAR2 really provided a motivation to develop this type of simulation technology, as we wanted to perform quick tests and a lot of tests through all the development phases of this satellite. So yeah, we had this need of performing those tests, even at the component level or going towards the subsystem level, the integrated level, even before all the hardware or even a single piece of hardware was present. So just to perform initial estimation with the simulation without the hardware. A few characteristics, some are shared with the other simulation technologies. For example, flexibility, modularity, or real-time support. A few others are interesting. For example, this software maintains the same functionality towards all the test phases and all the development of a satellite, at least for a CubeSat. Then this software provides automatic code generation and compiling in order to somehow exclude the user from the painful job of coding and then compiling the software. This is handled automatically in our simulation. Again, the user coding is limited to the models that are run inside the simulations. I will briefly guide you through the graphical user interface. It's quite simple and nevertheless allows you to perform different things. First of all, we can define the architecture of the simulation. This is a window that allows us to choose between different types of simulation, whether we want to include hardware or just perform software simulations, and which are the interfaces. Those are a few examples of what we can set as a parameters. Continuing, we implemented a simple drag and drop window to select the models we want to use and to adjust and correct the model flow in order to define for each process we are running to define the exact simulation flow. Few other parameters we can set, whether we want to perform real-time simulation or accelerated one, step time, few constants. Then we can save the output for post-processing and data visualization. I will now describe a few different simulations we can perform. Algorithm-in-the-loop simulation, for example, MATLAB, it's a type of algorithm simulation where in this case we have just one simulation process, everything is run on a simulator console and there is no hardware present at this stage. This is the block diagram shows the algorithm-in-the-loop simulation for the attitude determination and control system. For example, the software-in-the-loop simulation, we start to include the pieces of the final flight code, and we simulate how those pieces of software will interact inside the final satellite. So we simulate interfaces between few processes representing the microcontrollers on board. Again, this is an example, not going into the details. For controlling the loop simulation, we are now integrating the first piece of hardware, and it's the controller, where we load the flight software that we started to test in the earlier phase in the software in the loop simulation. Here are a few cases of communication between different boards in the satellite, or sensor testing for the IMU communication. Then we proceed to the full verification by including the satellite, but also including actuators, sensors in a algorithm-in-the-loop configuration. Again, the diagram. A few images that depicts the simulation we were performing. The results. For software-in-the-loop, in the earliest phase, we didn't really notice any error, everything was working flawlessly. Going to the control-in-the-loop simulation, we started to notice earlier in the development phase, a few loss of packets that were accounted with wrong coding or wrong models. And then IMU packets were lost for about 3% of the time, although our IMU sampling frequency is way higher, and this posed no error. Few results of really not detailed from our earliest simulations show packet losses everywhere, more or less, and this depicts control-in-the-loop simulation. So you can see a comparison between algorithm-in-the-loop and algorithm-in-the-loop simulation. We had different results at the beginning. Now, towards the end of the development phase, the results are converging together, and these were accounted for data corruption and other problems in the simulation configuration. Few results for the complete loop simulation. The graphs you see there are made from the data received from our ground station. It's a mobile ground station we have at Polytechnic di Torino, so they are not depicting the real behavior of the simulations. We were receiving packets not every second. The packets receiving was one every 2 minutes. Again, quaternions. This is just to see that actually our simulation were providing good results. The results were compared both with the SDK and MATLAB simulation in Simulink. They provided compatible if not equal results. And here battery charging during the simulation. We were providing, in this case, we can speak of EPS in the loop simulation as we were feeding the the external power simulating the solar input with the power supply controlled by the attitude dynamics and orbit dynamics of our satellite. And that's all. Thank you for the attention.
We have time for a few questions before the coffee break.
I would have one. One of the last slides about the solar power, if you can maybe go back, where you have these 5 panels. They were all in sunlight, or is it flat set testing, or was it in real configuration of one new CubeSat?
They were not in. They were.
At least it looks like that they were all exposed to.
No, they were in a flat configuration. Yeah, it is just depicting the eclipses and yeah.
Thank you.
Any other question? So thank you again.